The subject of this session is linear equations, and this is a quick review of material from an algebra class. The first set of equations are 2x plus y equals 15 and x plus 2y equals 15. If you make y the subject of both of these equations, the equations can be written as y equals 15 minus 2x and 2y equals 15 minus x, or y equals 7 minus 1/2 x. We can set the two equations with y as the subject equal to each other and solve for x and y, and we will get x equals 5 and y equals 5. Another approach is to set the equations up and solve them as simultaneous equations, in which case we want to eliminate one of the equations from the set. So what we do is we multiply the first equation by 2. 2x plus y equals 15 becomes 4x plus 2y equals 30. With the second equation remaining, x plus 2y equals 15, we can subtract one equation from the other, and we're going to set it up where we subtract 1x from 4x to get 3x. We subtract 2y from 2y, and the y's are eliminated. 2y minus 2y equals 0. 15 from 30 equals 15. So we get 3x equals 15. X equals 15 divided by 3 equals 5. We plug x equals 5 back into any of the equations, and we'll plug it back into the first equation. 2x is 10. Y equals 15 minus 10. Y equals 5. Y equals 5. We can now plug that back into any of the equations. So we get the second equation, x plus 2 times 5 equals 15, or x plus 10 equals 15, x equals 5. Again, there's more than one way to solve this pair of equations, but the reason we are doing it this way is because we want to actually draw the two straight line equations, and when we have graphed them, we want to identify the production possibilities set for the purposes of this exercise. Calculating the equilibrium is secondary. We want to be able to see what the sketch looks like. We've already determined that one equation will intersect the y-axis at 15 and the other will intersect the y-axis at 7.5. Correspondingly, for the x-axis, because of the symmetry in this equation set, we get one line intersecting the x-axis at 7.5 and the second one intersecting the x-axis at 15. In trying to identify the production possibilities set, we're going to go with the area which is below the two constraints, or the two straight lines, and that will define our production possibilities set. Getting back to the idea of linear equations, I'm providing another example. We are supplying a second set of linear equations here. 4x plus 2y equals 20. 5x plus 10y equals 70. When we solve this pair of equations, we get x equals 2 and y equals 6. The details of the calculation can be seen on the screen. I would expect that you would follow through. Again, our goal is to sketch these two equations, and the point x equals 2 and y equals 6 is the intersection of the two. But again, that is not nearly as important because the sketch is more important than any given point on the equation set. Notice that even though we started with larger coefficients, we could have scaled these down. For example, we could have divided the first equation by 2 to obtain 2x plus y equals 10. And the second equation, when divided by 5, gives us x plus 2y equals 14. 2x plus y equals 10, x plus 2y equals 14. Indeed, once you make the sketch, the large numbers you saw earlier will disappear because the equations simplify, to give you y as a function of x, and we get y equals 10 minus 2x and y equals 7 minus 1/2 x, regardless of the initial sets of coefficients. Part of the reason we are interested in commenting on this is because the initial sets of coefficients have a meaning in terms of the economics of it, the amount of hours it would take to produce 1 unit of a given product, or the amount of units of capital it would take to produce 1 unit of the same product. So the coefficients have a meaning that we need to understand, and that is beyond just the arithmetic calculations and the geometric and algebraic analyses. But the geometric and algebraic analyses help us to understand the final outcomes of the problem. We'll take the coefficients and now apply them to the problem we're working with, so we get out of the XY mindset and we come back to a problem that we are solving in class. And we have two industries, cars and textiles. We have resources, labor and capital, and the coefficients in front of the C and T variables represent input-output ratios. The problem we're looking at right now is the same as the very first problem we started with. X plus 2y equals 15 and y plus 2x equals 15, except we've changed the labels to C and T. And now we are looking again at the coefficients to interpret what they mean. ALC equals 2 and ALT equals 1. AKC equals 1 and AKT equals 2. L equals 15 million. K equals 15 million. And that is the setup for this problem. What we've added here is the production possibilities frontier in blue, and then we looked for an equilibrium by adding the indifference curve that sits tangentially on the production possibilities frontier that represents the highest level of satisfaction that can be obtained when there is no trade. So of all of the combinations of C and T that the country can have, the one it would choose is the one that maximizes its social welfare value, or represented by the highest possible tangential indifference curve. The economics here then is to ensure that all of the coefficients are meaningfully interpreted and that the autarky equilibrium can be identified. Notice that the intersection of the two lines is not urgent towards this answer because it has nothing to do with the intersection. It is the tangential equilibrium of the indifference curve and the production possibility that is our interest at this stage of the analysis. As we move forward to understand the dynamics, we're going to then get back to understanding and interpreting the full employment point, which is the intersection of the two blue lines that will help us to determine where the country will produce to fully utilize its resources. But if we could back up to the two lines again, focusing not only on the blue segments but on the entire straight line, we're going to identify one of these resource constraints as the capital constraint and the second one as the labor constraint, and hopefully we can easily take care of that because from the starting point we were told which equation represented the labor and which equation represented the capital. The point I want to make here is that the area between the two curves, whether it's to the northwest of 5,5 or the southeast of 5,5, we want to be able to interpret the area under the outer constraint and beyond the inner constraint. That would be an area where one constraint has been exhausted and there's still more units of the second constraint available, and therefore the country would, if it wants to get a consumption level in that region, that triangular region beyond the blue constraint, it would need to increase one resource or the other. And you can see how increasing the resource would shift it out parallel to where it currently is. So we can shift it out until it intersects the point we want, and that would be one solution to getting the level of consumption to be greater. But in this class, the focus is not on growing your resources, but on trade. So we want to ask the question, what does it mean to trade to some consumption bundle beyond your production possibility frontier? And that will involve moving away from the autarky consumption point. In this panel, it's labeled as E subscript A, to some point that is higher But if we went for a point that was strictly to the northeast of E subscript A, then we know that the country would be having a larger quantity of both C and T, and given the assumption that more is better, then any point to the northeast of the intersection of the indifference curve with the production possibilities frontier would represent a higher level of satisfaction, unambiguously. Hopefully you can trade your way from EA to some point to the northeast of EA, and that will show that trade is good. We say trade is good, but it is reassigning your production away from point EA to the full employment point and then trading your way back to that point that is on a higher level indifference curve than the one passing through E subscript A. So that's the introduction to the topic we're working on, and we use this linear approach because all of the Heckscher-Ohlin conclusions can be seen readily using the linear programming approach.